In this and in the next two lectures, we're going to give an introduction to differential equations. A differential equation is an equation relating an unknown function and one or more of its derivatives. And we've already seen equations that look like this. Our equation for population growth from exponential growth and decay is a differential equation. It said the derivative of p with respect to time is k times p itself. So this relates the unknown function p, the size of the population, to its derivative dp dt. And perhaps a more realistic model of population growth is given by dp dt equals k times p by 1 minus p over k. We also saw Hooke's law, which says that the force required to keep a spring extended x units beyond its natural length is equal to a constant times x itself. And of course, force translates to mass times acceleration, so if x is a function of time, if the spring is moving, then m times the second derivative of x with respect to time is equal to a constant times x, is our translation of Hooke's law in this case, which is a differential equation relating x to its second derivative. Other areas where you're going to encounter differential equations are when you're dealing with air resistance and drag force and changes in the stock market and other areas of economics and business. Here are some general examples of differential equations relating unknown functions y, which are functions of x, to their first derivatives. The order of a differential equation is the order of the highest derivative that occurs in the equation. So the differential equation 2 times the second derivative of x with respect to time is minus 10x has order 2 because the highest derivative there has order 2. And the differential equation, the derivative of velocity with respect to time is 32 minus 10 times the velocity squared, is a first order differential equation because the highest derivative in the equation has order 1. Now if we're looking for a solution to a differential equation, we're looking for some function which fits the equation, so that when I plug that function into the equation and its appropriate derivatives, then it solves the equation. If I'm looking for a solution to the equation y prime equals e to the x over 1 plus e to the x, in fact I'm just looking for an antiderivative for y, and I can figure that out using a substitution. One solution is given by y equals the natural log of 1 plus e to the x. And I could check this by checking that y solves the equation. When I take the derivative of y, it's actually equal to e to the x over 1 plus e to the x, so it fits the equation. We see that y equals x minus 1 is a solution to the equation y prime equals x minus y. And the reason is that y prime equals 1 here, so 1 is equal to x minus 1, and this fits the equation. We also see that y equals x minus 1 plus 1 over e to the x is also a solution to this differential equation, because if I take the derivative of this function, it's equal to x minus the function itself. So we see that this equation has at least 2 solutions, and in fact it has infinitely many solutions, and this ties in with what we've seen before for antiderivatives and for the differential equations we encountered in exponential growth and decay. dy dt equals 2 times y has an infinite family of solutions, one of which is given by y of t equals 10 times e to the 2t. And of course you can check that that's a solution by checking that its derivative is 2 times the function y itself. Now if we're asked to solve a differential equation, our aim is to find all possible solutions. So to find a description of the entire family of functions which solve the equation. And a general solution is a solution involving constants which can be specialized to give a particular solution. So the general solutions to the differential equations that we saw above, dp dt equals 2 times p, is p of t equals k times e to the 2t. And of course we've seen this solution before and worked with it in our section on exponential growth and decay. The general solution to y prime equals e to the x over 1 plus e to the x is the family of antiderivatives for this particular function. So it's y equals the natural log of 1 plus e to the x, the absolute value of that, plus any constant we can dream up. Of course, that's something we could have figured out in Calculus 1, and we see that it has an infinite family of solutions. And this equation y prime equals x minus y, which is something we'll be able to solve in the next couple of lectures, also has an infinite family of solutions, y equals x minus 1 plus c over e to the x. And the two we looked at on the last page are the solutions with c equals 0 and c equals 1. If we look at the antiderivatives of e to the x over 1 plus e to the x, are the solutions to the differential equation dy dx equals e to the x over 1 plus e to the x. Notice that for any given point, there's exactly one solution running through that point. For example, if the point is 0, the natural log of 2, then there's exactly one solution to this differential equation which runs through that point on the plane. In other words, it has y of 0 equals the natural log of 2. The value of the function at x equals 0 is the natural log of 2. And an initial value problem is a problem asking for a specific solution to a differential equation satisfying some initial condition, such as y of some specific value of t equals y naught, where y is a function of t. For example, suppose I know that the general solution of the equation y prime equals x minus y is given by y equals x minus 1 plus c over e to the x, and I'm asked to solve the initial value problem y of 0 equals 0, then I can use the general solution to figure out what the specific solution to this initial value problem is. So whatever that solution is, it must look like y of x equals x minus 1 plus c over e to the x for some c. And also, when x is 0, we must have y of 0 equals 0 minus 1 plus c over e to the 0. So we must have y of 0 is c minus 1. But we're looking for that solution where y of 0 is 0, so we must have c minus 1 equals 0 or c equals 1. So our precise solution is given by y of x equals x minus 1 plus 1 over e to the x, and this is the unique solution to this initial value problem. Now, suppose we didn't know what this general solution was, then we would have a problem finding a solution to this initial value problem, and at the end of this lecture we're going to look at a numerical method of estimating a numerical solution to this problem.